Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, I'm going to work through my notes on irrational zeros of polynomials. So again, this is a lesson that I already taught with my students, but I wanted to kind of work through the notes, and so I'm going to kind of go through these slides and kind of show my work, and then hopefully my explanations here, if you are interested in learning about irrational zeros, is going to benefit you. So let's go ahead and get started. So basically, what we're going to talk about in this lesson is learning how to determine the irrational zeros and multiplicity. We're going to determine how to determine all the zeros given a factor or a zero. We're going to learn how to apply the remainder theorem as well as the factor theorem. And then we're going to learn how to write the equation of a polynomial given irrational zeros. So the way that I kind of start off this lesson is I want a student to go ahead and find the zeros and then go ahead and write the linear factorization. Now, first of all, we look at these and I said without factoring. So I said, all right, guys, these are non-factorable. Let's make sure we can do this. And so the main thing I want students to come away with this is first setting up the equation. If we're trying to find the zeros, then we're going to set our equation equal to 0. Well, the nice thing here is since we only have one variable x, then I can just set x squared is equal to 7. And then now, if I want to solve for x squared, I'm going to use my inverse operations. And then I had to make sure that I since I'm introducing the square root, that was plus or minus the square root of 7. So those are your zeros. However, we wanted to go ahead and write the linear factorization, right? We wanted to write the products of these zeros. So what I did was, if I remind students in last lesson, we learned how to write the factors, write the polynomial given the zeros. And this would be the same case. Like if I wanted to write the factors, like there's the zeros, right? If I want to write this as linear factorization, we could write them as x equals square root of 7 and x equals negative square root of 7. All right, then we can write these as factors equal to 0, right? That's where they kind of came from. And you can see that those are going to be the two factors. So the linear factorization would just be f of x equals x minus square root of 7 times x plus the square root of 7. So this is a way of writing the linear factorization when given the zeros. So if you can figure out the zeros, you should be able to write the linear factorization because then we just multiply that to get the polynomial. My goal is by the end of this lesson that you'll be able to look at this and understand that is the factored form, right? So you can look at this and say, oh, that's a difference of two squares across irrational numbers. Now for the next example, so for this one, we add 7, take the square root, right? But this one, we don't want to add 2 and then take the square root because there's more than one variable. We have a x squared and we have a negative 2x. So we can't use inverse operations like in the last one. And so what we need to do is go ahead and use the other way that we learned how to solve quadratics without factoring, or use the inverse operations, which is the quadratic formula. So a couple things I wanted to remind students of, the quadratic formula, remember, is x equals opposite b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay, now again, the a, b, c, those all come from when you have a quadratic equal to 0 in standard form. So ax squared plus bx plus c. So that's where the quadratic formula, or at least let's write over here. That's where the quadratic formula, that's where those a, b, and c come from. So make sure it's in that format if you're going to go ahead and be doing that. All right, so here we have a quadratic equal to 0. So therefore, I can recognize my a is going to be 1, my b is negative 2, and my c is negative 2. Since this is like an Algebra 1, Algebra 2 standard, obviously that's why we kind of immediately get right into it. However, I will state that a lot of students still make a lot of mistakes here with the quadratic formula. That's why I would highly recommend, until you get really, really used to working with it, especially if it's been a while since you did the quadratic formula, is just to write down all of these numbers, like write everything out in parentheses. 2 times a, which is 1. Okay, so that's opposite of b plus or minus square root of b squared minus 4 times a times c divided by 2a. And when we go ahead and simplify this, we get now it's going to be a positive 2 plus or minus the square root of 4 plus 8 divided by 2. And therefore, that can now be simplified into x is equal to 2 plus or minus the square root of 12 divided by 2. So then the one thing we talked about is, simplifying the radicals. And, this is something that we did in our skills practice. So I gave my students some practice on the skills practice for this. But just make sure that we can break up the square root of 12 into the square root of 4 times 3. So therefore, that's going to be 2 radical 3. So that's just going to be a little side work that I worked with my students. So by simplifying that way, I have 2 plus or minus 2 square root of 3 divided by 2. Now that 2 can divide into both those terms, and I'm left with 1 plus or minus 2 square root of 3. Now the interesting thing here is, again, remember these are the solutions. These are the zeros. So, oops, I'm sorry, that's a plus or minus, right? So technically we have x is equal to 1 plus 2 square root of 3, and x is equal to 1 minus 2 square root of 3. So if I wanted to set these equal to 0, like I did over here, I need to subtract the 1 and subtract the 2 square root of 3. So therefore it would be x minus 1 minus 2 square root of 3 equals 0. And here I'd have to subtract a 1 and add that. So it'd be an x minus 1 plus 2 square root of 3 equals 0. So now you can see my linear factorization, which I'm kind of running out of room here. Let's just do the linear factorization is going to be f of x equals 1 oops. Oh, let's just put up here. Why not? Is going to be x minus 1 minus 2 square root of 3 times x minus 1 plus 2 square root of 3. Okay, so you can see how I've written that out as a product of its factors. And this is something that's going to come up again and again in today's lesson. It doesn't look as nice and as pretty as writing these factors, but they are nevertheless also factors. So that was that linear factorization. And basically, I just want to remind students there's really kind of two ways to do linear factorization. So, first way is if I had like x squared minus, x minus 2. The nice thing to do linear factorization is just to factor things. And that's the goal that I want us to kind of get to, is writing the linear factorization in the factored form, which is b, x minus 2 in this case times x plus 1. There you go. That's the linear factorization, right? So this is your standard form. That's your linear factorization. However, the way that we kind of did it here, which is irrational numbers, and again, we did the exact same thing here last lesson. If I gave you like x equals 1, x equals negative 2, x equals 3, or if I said here's the zeros, 1, negative 2, and 3, right? So if I give you the zeros, you can set the zeros equal to x and then set them equal to 0, and that is going to tell you what your factors are. So then I can call my f of x here. It's just going to be x minus 1 times x plus 2 times x minus 3. So that's kind of like the backwards or the opposite way of doing the linear factorization, is basically just taking our information, if we're given zeros, writing them as factors and then multiplying. So sometimes factoring is not going to be as obvious. So as long as we find the zeros, we can work our way backwards. But there are some things we got to be careful with that, which will come up kind of through the lesson. All right, so the next one is then I gave some students some ones that were factorable. And what I wanted students to do was, again, find the zeros, same directions here, find the zeros and then write the linear factorization. All right, so let's kind of go back to our factoring techniques. Again, remember, for right now, let's just try to think about, well, how would I factor this if I didn't have it to the fourth power? What if it was x squared minus, 3x plus 2? Well, that would be factorable to x minus 2 times x minus 1. So this is going to be the same thing. I'm just going to be raising the powers. So 0 equals, x squared minus 2 times an x squared minus 1. Now, there's a couple different ways we could do this. Hopefully you recognize here I can factor these both down. Some people, might be a little bit hesitant as far as identifying this. So again, we can kind of go back to like old school. Like, how did we figure out this? Now we have a product equal to 0. So you can use the zero product property. X squared minus 2 equals 0, and x squared minus 1 is equal to 0. So therefore, you'd have, x squared is equal to positive 2, x squared is equal to positive 1, square root, x equals plus or minus. Here, I'll just introduce the square root. So x equals plus or minus the square root of 2, and x equals plus or minus 1, because obviously the square root of 1 is 1. So those are my zeros. And then now I can just write those as factors. Or if you think about this, like if I was going to write those as factors, I would just be x minus the square root of 2 times x plus the square root of 2. And then times x minus 1 times x plus 1. But you can skip a lot of the steps. You can literally just factor these using difference of two squares, and you can see now that's just writing that in that factored form. So it's the kind of same idea. All right, so let's go ahead and do another one here. In this example here, I'm going to set it equal to x now. I notice that I have a 2x squared that's in common, so I'm going to factor out 2x squared. That's going to leave me with an x to the fourth minus 9x squared plus 8. And again, we want to go ahead and figure out what it is we can factor that out. So if I just did this as x squared minus 9x plus 8, I would recognize that that's factorable to x minus 8 times x minus 1. So now we're just going to raise the factors here. So 0 equals 2x squared times x squared minus 8 times x squared minus 1. And if you were to multiply that out, you can see how it would work. Now there is one important thing here is I'm going to factor these across, but I'm going to do a little side work here. Because if I had x squared, like I can set these now equal to 0, right? But I already know that this is a difference of 2 squares, so I'm just going to do that one easily. But if I had x squared minus 8 is equal to 0, that if x squared is equal to 8, you square root, x is equal to plus or minus the square root of 8. But again, remember, we can simplify that, right? So x would equal plus or minus 4 times 2, which would equal x is equal to plus or minus 2 square root of 2. Now again, remember, those are two zeros, right? So we can write these, and I'm just going to break this up, 2 square root of 2, and then we could say x is equal to 2 minus square root of 2. Oops, I'm sorry. Negative 2 square root of 2. And then we could write those as the factors. So the factors okay, so hopefully you can see how that is what my factors would be. So now when I write this in factored form, I still have the 2x squared, but now I'm going to have an x minus 2 square root of 2 times an x plus 2 square root of 2. And then we have an x minus 1 and an x plus 1. All right, and therefore now my zeros, I have 0, right, because that's that x, and however it's raised to a 2, so that's going to be a multiplicity of 2. And then I'm going to have plus or minus 2 square root of 2 and plus or minus 1. All have multiplicity of 1. The next example here is going to be by grouping. So therefore, I'm going to group the first two terms and group the second two terms. And again, notice that it's 4 terms. So that's why I'm going to use the grouping technique. I'm going to factor out the term that they have in common here, which looks like a x squared. Now I see a negative, and sometimes we want to get rid of the negative. So, in this example, why don't we factor out the negative, and then the next example, I'll leave it in there, and we'll see the difference. So if I factor out the negative 3 in this case, or negative 3x squared, that's going to leave me now with a positive x. Oh, not a negative 3x squared. I'm sorry. We can only do a negative x squared, right? So therefore, if I factor out a negative x squared, that's going to leave me now with a x minus 1. Okay, and just make sure when you multiply about that works. So if I want to get a negative x minus 1, that means I have to multiply by a 5, or factor out a 5, x minus 1. Now you can see that both of these expressions have an x minus 1 in common. So if I factor out the x minus 1, that's going to leave me with a negative x squared plus 5. Now I can't really do anything with a negative x squared minus 5, but what I can do is I can factor out the negative. And that becomes really, really, really important. Because when you factor out this negative here, now you can see that again, it's a difference of 2 squares. I can factor that down. So my linear factorization here is going to be a negative x minus the square root of 5 times x plus the square root of 5 times x plus 1. And therefore, if you're going to find the zeros, it's just going to be plus or minus the square root of 5 and negative 1. Now, the reason why I bring this up is because once you have it at this point, you could set these both equal to 0, right? And if you set negative x squared plus 5 equal to 0, again, you're going to subtract 5, divide by negative 1. You're going to get x equals plus or minus the square root of 5. The problem comes in is when you write this as a linear factorization, you're going to have this factor, that factor, and you already have that factor. But you got to be careful to understand that there's that negative there. And again, my point that I want to bring up is remember the linear factorization is just the problem factored out. If I multiply this times this times this, I better get my original function, right? I better get that negative 3x or negative 3. And again, you can see that is where is, oh, my bad. I was like, no wonder I'm not getting 3x. What happened when I factor out a negative 3x? That was supposed to be a 3 right there. My bad. I forgot there was a 3 there. So all of these have a 3. I just forgot about the 3. 3x minus 1. So that becomes actually a positive 1/3. Where did I get -1? I was going crazy. I did that horribly. So when you set 3x minus 1 equal to 0, you should get a positive 1/3. There you go. That's why you got to be a little careful here, right? But again, if I multiply this out, I should get a -3. And you can see by me checking my work, I recognize, oh, not only do I need to make sure it's negative, I need to get a 3. So where'd the 3 go? And that's why I realized I did a factor wrong. So important point. You can check your work with that linear factorization. All right, so the next problem, we notice that it's not in standard form. So you don't need to do this, but I like to do this. Just go ahead and rewrite it. X squared plus 3x plus 3. Now, in this one, I factor out the negative. In this case, I'm not going to factor out the negative. So let's just factor out an x squared. And by factoring out an x squared, I'm going to be left with a negative x plus 1. And again, in this case, now we need to, again, factor out we need to make this to be a negative. So therefore, I'm going to factor out a -3. And that will give me, oh, that's supposed to be a negative. Be careful when you rewrite this in negative form. Notice how that's a -3x. So that should have been a negative. I just wasn't paying attention. All right, so now when I factor out a -3, that leaves me with a negative x. That'd be plus 1. Now you can see that these are going to be the same. So 0 equals a negative x plus 1 times an x squared minus 3. Now again, if you use the rules of exponents, like if I multiply this out, that's fine, right? But hopefully you recognize if I just need to write the linear factorization, I can leave this here. I just need to factor this one down, right? And it's just very important because if you were to solve this, you would get the 0 as 1 and plus or minus square root of 3, and you would probably forget that there's that negative there. So it's just kind of important, when you're finding the zeros, that's fine. Like go ahead and set negative x plus 1 equal to 0. And, x squared minus 3 equal to 0. So -1. So x is equal to 1. And x is equal to plus or minus the square root of 3. Just be careful. The linear factorization, though, needs to include that negative, right? Because when you need to get a negative x cubed in front. So I'm just going to leave that factor as it is. I'm not going to write it as x minus 1, right? Because if you were to write this as a factor, you'd write x minus 1 equals 0. And therefore, but again, you have to have that multiplied by a negative. And it doesn't matter if it's multiplied by a negative here or if we multiply the negative on the difference of two squares. It doesn't matter where it is. You just need to make sure it's there. And therefore, this would be x minus square root of 3 times x plus the square root of 3. Okay. So that was kind of a review of Lisa's factoring. All we're really doing now is just finding those zeros and the linear factorization. But really the main point that I wanted to come around with the students was understanding division. And so I kind of broke it up in these multiple of questions. I said, if 3 is a factor of 12, then what? And, a couple things we said. Well, if 12 is a factor, that means you can divide 3 into 12 and evenly. Or, you could see the answer is 4. So we could say, 12, we could write division like this. We could even do the old school way, the long division way, if you remember. 3 divides into 12 evenly 4 times. And another way, really the main important thing to understand was 3 times 4 is equal to 12. So if 3 is a factor, that also means that 4 is a factor, right? That's a factor, and that is a factor. And that is something very, very important. If 3 divides into 12 4 times, that means 4 is also a factor. That means 3 times 4 is equal to 12. Very, 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 very important for us to understand about that. So because really that's all we're doing in the rest of this lesson is we're just expanding on that. So if I say x plus 1 is a factor of x squared plus 3x, that means I can divide x plus 1 into x squared plus 3x. So a way that we might write that would be like x squared plus 3x plus 2 divided by x plus 1 times. Now, 3 divides into 12 4 times. That's pretty obvious for most students to remember. How many times does x plus 1 divide into this? Well, that might not be as obvious for students, but we've done problems like this before where we can simplify this. I recognize the trinomial here. So I said, well, any trinomial can be, is going to be we can look to factor it first. In this case, I would factor this to x plus 2 times x plus 1. So x plus 1 indeed divides into x squared plus 3x plus 2, x plus 2 times. That means that x plus 1 times x plus 2 has to equal x squared plus 3x plus 2. And that makes sense, right? We know that x plus 1 times x plus 2 equals that. Like that's the factored form. But it's just important that if we know that x plus 1 is a factor, not only does it evenly divide into that polynomial another factor times or another polynomial times, but also you can write any polynomial as a product of its two factors. Now, not every problem that we're going to be able to do is going to be this obvious and this easy to work with. So therefore, we have to rely on how else could we do division if we can't like simply factor everything out. So there's two basically methods that we're going to work with division. The first one is going to be long division. So long division is kind of like our pure division, all right? So when we're doing long division, basically all we're going to do is we're going to take your divisor, and actually let's kind of do long division here. So we have our divisor, our dividend, and this is our quotient. Okay. So the divisor is what you're dividing by, which is, we're going to take an x plus 1. And then we're going to divide that by x squared plus 3x plus 2. Okay? So in this case, when you're dealing with a divisor, or when you're doing long division, remember this is your factor. So yeah, I'll go through this in a second. So that's going to be our factor, what we're dividing. A couple of things, make sure that you have your divisor and dividend in the standard form. And we're just going to divide x into x squared. So x divides into x squared, x times. Now, some students get confused on that. So a lot of times I just like to write it vertically like this. X divides into x squared how many times? You could say, oh yeah, x times. Then you take your first term of your quotient and you multiply times both terms in the divisor. So let's do it like that. So x times x is x squared, x times 1 is x. Then what we do is we put around parentheses and you subtract rows. Sometimes people like to put a place value here like 0, and that's fine. You don't need to do it, but sometimes it's helpful. And then you subtract just vertically. Just make sure I like to put things parentheses because x squared minus 0 or minus x squared is just a 0x squared, which we don't really need, but we'll just write it there first time. 3x minus x is going to be a positive 2x, and 2 minus 0 is positive 2. So that is like round 1, okay? So now that is completed one round. And now we basically just do the exact same thing again. X divides into 2x how many times? How many times does x divide into 2x? Well, that divides into there x amount of times. Or I'm sorry, 2 times, not x. Geez, I'm making the same mistakes I tell my students. It goes in there 2 times. And we already know the answer is 2, guys. So it's x plus 2. Then, just like I multiplied x times both these terms, I'm now going to multiply 2 times both those terms. So 2 times x is 2x, and 2 times 1 is 2. Now, the important thing to understand here is when we're subtracting these, obviously we're going to get 0x and we're going to get 0, right? That's the remainder, right? And we need to have a remainder because if we're saying something is a factor, it better divide into there evenly. And if it doesn't, it's either not a factor or we made a mistake. So, and typically we want to watch if our, making a mistake. But you can see here that is our answer, x plus 2, which we already knew, okay? Now, the other technique is synthetic division. And we're going to talk about, when to use long division, when to use synthetic division in this class. But synthetic division is a little bit different. Synthetic division, instead of using a factor, synthetic uses a 0. So my main point, okay. So if here's x plus 1, when we're doing synthetic division, we're going to use the zeros. So here's a factor. If you set that equal to 0, then you would get x equals -1, right? And I'm going to talk about this in the next slide. But basically, I just want to kind of run through synthetic division here real quick. So you're going to take the 0, and then you're going to take the coefficients of the dividend. So the coefficient dividend is 1, 3, 2. Hopefully you see where the 1, 3, and 2 come from. So you take the factor. The 0 would be -1. Right? So you can see where I got the 0. I basically set the factor equal to 0. And then you take the coefficients of the quotient. Now for synthetic division, you bring down, the first term you bring down, and then you multiply on the diagonal, add on the vertical. And this, the reason why synthetic division is preferred, you can think, guys, you're adding and you're multiplying. A lot easier than dividing and subtracting, right? However, we'll see why it's not always going to be preferred. So, bring down to 1. 1 times -1 is -1. This becomes 3 plus -1 is 2. 2 times -1 is -2, and 0. So that is your remainder, that is your constant, and that is your coefficient of your linear term. And we already know the answer is x plus 2, right? So now we just need to decipher that into x plus 2. And that's where a lot of students, kind of get a little, confused on this process because we don't know, what, you got to remember these are your constant and your coefficients. So that is at least the synthetic division, away from that. And again, the really idea of using long division for synthetic, it's kind of like long division, synthetic division. You know, if x plus 1 is a factor, then x equals negative 1 is a 0, right? Because if I had like x minus c is a factor, well, again, all we do is we set our factors equal to 0, and we'll get x equals c is the 0. So it doesn't matter what your factor is, just make sure you set them equal to 0 and solve. And a lot of times we can do this in our head to be able to find the zeros. All right, so now we have another factor. Now again, if I wanted to use synthetic division, I just need to figure out the 0. Well, the 0 would be, you know, if you set that equal to 0, so you've set 2x plus 3 equals 0, you can see that my 0 here is going to be x equals negative 3/2. So a lot of people are like, oh, I'm just going to do synthetic division. But then I show them synthetic division with a fraction, and they're like, I probably don't want to do that. Maybe you should, maybe you do, maybe you don't. But guess what? For this, I'm actually going to do it both ways so you can see the benefits of synthetic division, also what you need to watch out for. Because you can use synthetic division with the 0, you just have to be a little careful. But first, let's do long division, because long division is something that I feel would probably is not too difficult for this problem, and it's going to be preferred. So I had 2x cubed plus 13x squared plus 27x plus 18. All right, so I'm going to go ahead and work through again the process. I'll do it a little bit quicker from there. But again, make sure everything's in standard form. You're always going to divide your first term into your first term there. So again, like how many times does 2x divide into 2x? Well, you can see that goes in there x squared times. X squared times 2x is going to be a 2x cubed. X times 3 is going to be a positive 3x squared. Now again, you could write 0x and 0 here if you want to, but in this case, I'm just going to subtract my rows and not worry about them unless I need them. So 13x squared minus 3x is going to be a 10x squared. So again, how many times does 2x divide into a 10x squared? Well, 2 divides into 10 5 times, and x divides into x squared x times. So that's going to be a 5x. Okay, so 5x times 2, and 5x times 3. So 5x times 2x is going to be a 10x squared, and then 5x times 3 is going to be a positive 15x. Now I can bring this down, right? So that's a 27x. And now I can just subtract my rows, and that's going to now leave us with a 12x. 2x divides into 12x. 12x divided by 2x. Well, that's going to be a positive 6 times. So 6 times 2x. I'm not going to do this anymore. This is kind of like getting crazy, as you can see. 6 times 2x is going to be a 12x. And 6 times 3 is going to be a positive 18. Okay? Then you bring all that down. And now if you subtract your rows, we better get a 0, which of course we do, which is our remainder. But the important thing here is that we now know that since 2x plus 3 evenly divides into this polynomial, it is a factor of that polynomial. And if 2x plus 3 evenly divides into this polynomial, x squared plus 5x plus 6 times, that also means x squared plus 5x plus 6 is also a factor. That means I can write my polynomial now as f of x equals 2x plus 3 times x squared plus 5x plus 6, right? Now again, we've been practicing writing the linear factorization. This is not a linear factorization. That is linear, this is not. Well, fortunately for us, I can further factor that down. 2x plus 3, and then this would be factored into x plus 3 times x plus 2. And the nice thing again about the linear factorization is I can just go ahead and determine all the zeros. I can set these equal to 0 on my own and find the zeros. Okay, so there you go. It wasn't too bad, but you got to be comfortable working with the long division. So let's go ahead and do this on synthetic division and see what we have to know when we're dealing with a fraction and synthetic division. So if I do negative 3/2 as my 0, right? So you got to make sure you're using the 0, not the factor. And then I'm going to use 2, 13, 27, and 18. Okay, so you bring down the 2. Remember, 2's in the numerator, 2's in the denominator. So 2 times negative 3/2 is going to be a negative 3. 13 plus negative 3 is going to be a positive 10. 10 times negative 3/2, you can divide the 2 into 10. It's going to be 5. So it's going to be negative 15. that gives you a positive 12. 12 times negative 3 halves, 2 divides into 12 6 times. So it's going to give you a negative 18 and 0. Now again, we know the answer is x squared plus 5x plus 6, right? But if we were to write the answer here, you would see that it's not the same. Okay, that is not the same as this. So we have to understand that to get our final answer when we have this fraction is we have to divide it by 2. And again, you can always like check your answer. You know that if you were to divide 2x into 2x cubed, like that first term is going to be an x squared. So when we have the scalar of 2, if we just divide everything by that 2, then we'd get our final answer of x squared plus 5x plus 12. Okay, so it's just something to make sure that you are aware of. You know, synthetic division, again, it's we use it as a tool to help us do division, but we got to make sure we understand what the quotient is going to be, and then obviously to make sure it makes sense in our answer. All right, now the next one is I'm not going to do synthetic division for this problem because the zeros in this case are going to be x equals, plus and minus the square root of 3. And I used to teach it this way, but I just don't want to do it. It takes too much time, and there's too many opportunities for students to make mistakes. But basically, you need to do synthetic division with the square root of 3 and negative square root of 3. And for most students, it's not worth the time or the effort. So what I'm going to do is I'm not going to compare my answers with synthetic division here. I'm just going to do long division and make sure that I get a factor of 0. So I'm going to say x squared minus 3. And let's just do this long division here. So this is an example. Most students don't want to do synthetic division with a fraction, right? It makes sense. I understand it. Do long division. Most students are not going to want to do synthetic division with radicals, plus or minus square root of 3. So therefore, you can see how long division, making sure that you know long division and not rely on just synthetic division, is going to be very helpful and important. All right. So again, we got to understand our division here. X to the 4th minus x squared. Or I'm sorry, not x. No, you're division, not subtraction. How many times does x squared divide into x to the 4th? Well, that's going to be x squared times, right? Using the rules of exponents. So then x squared times x squared is x to the 4th. And x squared times negative 3 is a negative 3x squared. Now, again, it's really important that you don't put the x squared under the x cubed. Those are not like terms. You can't subtract those. So I'm going to use, in this case, I'm actually going to use a place value just so we can kind of see what I would do. Now, it's very, very important to use your parentheses in this case because the number one mistake students will have, besides not being able to divide this correctly, the second mistake students will make is they'll do negative 4x minus 3x to give you negative 7x. Well, no, it's negative 4x squared minus a negative 3x squared. That turns to a positive, so that's actually a negative x squared. And then negative x cubed minus 0x cubed, that's a negative x cubed. All right, and in this case, I'm just going to bring down everything. This is another way you can do it. You can just bring down everything every time the row. X squared divides into a negative x cubed. That's going to be a negative x times. Negative x times x squared is negative x cubed. And negative x times negative 3 is going to be a positive 3x. So again, you subtract your rows here. And this can give me a negative x squared plus 1. X squared divides into a negative x squared minus 1. Negative 1 times x squared is a negative x squared. And negative 1 times negative... Oh, I'm sorry. I forgot to change this problem. I always do that. I did this in class, and I still have just been so lazy. I just didn't want to change it. But that answer is probably supposed to be a 3. I keep on forgetting to change it. But I'll go back into the original slide and change it. So anyways, that should have been a 3 right there. And I was like, make sure you change that before you start the video. And of course I didn't. All right. So anyways, that's going to be a 0. So again, we figured out, hey, this is a factor. X squared minus 3x divides into this x squared minus x minus 1 time. So therefore, we now know that we can write this as a product of its two factors, right? Just like if 3 is a factor of 12 4 times, that means 3 times 4 is 12. So I can write this as a product of its two factors. Now, I could set these both equal to 0 and solve. However, hopefully I recognize at this point that here, this is going to be x minus square root of 3 times x plus the square root of 3. And if I were to set that equal to 0, I'd recognize it's non-factorable. Therefore, I need to use the quadratic formula for this one. So if I had x squared minus x minus 1 equals 0, I'd be like, crap, I need to now use the quadratic formula here. So let's go ahead and do that. So hopefully this one's factorable. You can see how that is. So therefore, x has to equal, let's do this a little bit quicker here. So that's 1 plus or minus square root of negative 1 squared minus 4 times a times negative 1 divided by 2 times a. All right, so x equals 1 plus or minus. That becomes a 1 plus 4, so that's going to be a 5 divided by 2. We can distribute this a little bit further, so I could do x equals 1/2 plus or minus 1/2 square root of 5. Now again, if you remember, I just talked about this at the beginning of the lesson, we can write this as factored form, right? So again, we can write this as x equals 1/2 plus 1/2 square root of 5, and I can write this one as x equals 1/2 minus 1/2 square root of 5. So therefore, to write my factored form here, then that's going to be x minus 1/2 minus 1/2 square root of 5. And this one would be x minus 1/2 plus 1/2 square root of 5. Now, as far as the zeros go, that can just be done as plus or minus the square root of 3, as well as, let's see, 1/2 plus or minus 1/2 square root of 5. So you can see here that obviously there's going to be 4 zeros. That was important. But you can see that linear factorization looks really, really weird. But again, that's something we've already kind of covered. And again, if something's not factorable, then you're going to want to use quadratic formula. So now here comes a case. And this one kind of becomes very important because remember, long division was factors, 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 factors. Well, now we're given zeros. So typically, we're going to want to use synthetic division. However, it's important for us to understand that if I give you the zeros, you can write them as factors and do long division. If you don't like synthetic division, you can always write the zeros as factors, right? If x minus negative 2 is a 0 and x equals 3, that means x plus 2 is a factor and x plus 3 is also a factor. Now, if we think about this, if we were to write 2x to the fourth in factored form, I think you'd agree that we're going to have at least 4 factors, or we're going to be using multiplicity, right? But as far as the linear factorization, we're going to have 4 of them. So if I only have 2 of them, what that means is if I were to multiply these, x squared plus 5x plus 6, that is also going to be a factor, right? Because obviously that gives you x squared. X squared is still going to divide into 2x to the fourth. And the way I kind of think about it is like numbers. Like if you have 12 divided by 2, I'm sorry, not 12. 24. If you have 24 divided by 2, that gives you 12. And you could still further factor down 12 by dividing it by 3 or dividing it by 4, right? So if I said 2 factors of 24 were 12 and 3, well, yeah, and 12 times 3, or not 12 and 3, 3 is not a, yeah, 3 is. 12 times 3 is 6, and you could say that 6 is also a factor of 24, right? So that's the same kind of idea here. Since these are linear factors and we have something to the 4th power, I can multiply these two to give me a factor. Now again, most students are not going to want to do this, but I'm teaching this for an important point, which is going to come up to the next problem. But for right now, what I told students, you have a zeros. Most students didn't want to use synthetic division, which was a good choice. Most students don't want to use fractions for synthetic division. Probably a good choice. But when you have an integer, let's roll with it. So I'll just take the 0, and then you take the coefficients. So that's going to be 2, negative 5, negative 11, 20, and 12. Okay, bring down the 2. 2 times negative 2 is going to be a negative 4. Negative 5 plus negative 4 is a negative 9. Negative 9 times negative 2 is going to be a positive 18. Negative 11 plus positive 18 is a positive 7. 7 times negative 2 is a negative 14. 20 plus negative 14 is a positive 6. 6 times negative 2 is a negative 12. Okay, now we got to decipher again what this information is. So that's your remainder, constant. That's not a constant. Constant, linear, quadratic, cubic. Okay, so x minus 2 is the 0. That means x plus 2 is a factor, right? So x plus 2 is a factor, right? Because obviously we got a remainder of 0. That's good. And obviously we already know x plus 2 is a factor since negative 2 is a 0. Now, it'd be great if we could factor this further down. But if I look into grouping the first and the second two terms, I realize this is not factorable. So therefore, what I'm going to need to do is break this down. It's like taking 24, dividing by 2, and 12. 12 is a factor, but you can further factor down 12, right? You can write these numbers as a product of their primes. Writing the prime factorization of a number is like writing the linear factorization of a polynomial. You can continue breaking it down. So I'm going to take my next 0, which is 3. That's supposed to be a negative, by the way. That's a negative 3. So that was supposed to be a negative x minus 6. That's also a factor. But anyways, I'm going to take 3. And now let's break this down one more time. So now I'm going to take the coefficients of my factor, not the coefficients of my original, right? If you want to find the prime factors of 12, you don't just take 12 divided by 3 and then 4 divided by 3, because you already know the other answers are 4 and 3, right? You take 12 divided by 4 or 12 divided by 3, which gives you 4, and then you divide that by 2. So we're further breaking down the factors. That's why I'm taking the coefficients of my quotient, not a back of the original problem. And then I do 2, bring down the 2. 2 times 3 is 6. Negative 9 plus 6 is going to be a negative 3. Negative 3 times 3 is going to be a negative 9. This gives you a negative 2. Negative 6 equals 0. Now again, since I'm not dealing with a fraction, I don't need to worry about the, dividing out my terms here. So that is my remainder. That is my constant. That is my linear. And that is my quadratic. So again, there's my factor. Now I already know x plus 2 is a factor. And obviously now I divide it into the x minus 3. So I know that is a factor. So let's go, and then here's another factor. So let's write out my factors here real quick. So right now I already have x plus 2 and x minus 3. You better write those because they're given to you. Then by doing division twice, I also get this factor, 2x squared minus 3x minus 2. Okay? And now if I just want to do one more step to find the linear factorization, I have to factor that down or use the quadratic formula. So let's see if we can factor this down. We know it's going to be factorable into a product of two binomials. And I see the answer here. I want to get to 4. So therefore, I'm going to do a negative 2 and then x plus 1. And let's see, let's make sure that multiplies everything, and that works. So therefore, there's linear factorization, and my zeros now are negative 2, positive 2, or I'll just do plus or minus. So plus or minus 2, 3, and negative 1/2. Okay? And if you would have done long division, doing this case, the nice thing when doing long division is you already would have included those two factors. So by doing long division, your quotient just would have done this. So, it could be a debate, doing long division or synthetic division twice. One might be easier, one might be harder. One might be harder for you. But the reason why, again, I wanted to go through that is because, what if I have a 0 here? I don't want to do synthetic division with this, right? So, but again, I don't want to do long division with a factor x minus 2 square root of 3 either. Like, that does not sound like fun either. So it's important for us to understand that what we call the conjugate pairs. If x equals 2 square root of 3 is a 0, then x equals negative 2 square root of 3 is a 0. And that's something very, very important to understand because remember, radicals come from, like on the first example we did, x squared equals 7. When I introduce the square root, we get x equals plus or minus the square root of 7, right? You have to include the positive and the negative, which we call our conjugate pairs. So this is important because if this is a 0, that means that's a factor. Well, that means this also has to be a factor. Well, now, again, that's going to give me an x squared, which will still be factorable into this x to the 4th. Now, if I multiply this out using distributive property, I'm going to get the same answer if I recognize, oh, this is just a difference of 2 squares. Multiply the first two terms, multiply the second two terms, and negative 2 times positive 2 is a negative 4. 3 times square root of 3 times square root of 3 is going to be a positive 3, and that's going to give me x squared minus 12. So that is also a factor. So that is what I'm going to use my long division for. So I'm just going to take x squared minus 4, or 12, sorry. Okay, and we're going to divide that into x to the 4th minus 14x squared plus 24. Okay, so x squared divides by x to the 4th. X squared times x squared is x to the 4th. X squared times negative 12 is a negative 12x squared. Again, subtract your rows here. That gives us a negative 2x squared. X squared divides into negative 2x squared, a negative 2 times. Negative 2 times x squared is a negative 2x squared. And negative 2 times negative 12 is going to be, again, a positive 24. Bring that down. And you can see now when we subtract our rows here, we get 0. So we have x squared minus 2 is also a 0. So therefore, I can write my f of x as being, x squared minus 12 times an x squared minus 2. But hopefully, we feel comfortable. We already know what this is written as factored form. And then hopefully, you don't need to set that equal to 0, but you could factor that to give us. So we have x minus 2 square root of 3 times x plus 2 square root of 3 times x minus square root of 2 times x plus the square root of 2. And therefore, my zeros are going to be x equals, is going to be plus or minus 2 square root of 3 and plus or minus the square root of 2. And there you go. So that is how that's how we can use division, guys, long division as well as synthetic division to go ahead and find our zeros. Now, the next two theorems kind of build on what we have described here, the factor theorem. Basically, the factor theorem says, if a polynomial function fx has a factor x minus k, if and only if f of k is equal to 0. Now, again, remember, what is k? Well, if x minus k is a factor, then x minus k equals 0 gives us x is equal to k. So k is a 0, okay? Or what we call a potential theorem. And again, if you plug that value k into your function and you get 0, then that tells you it's a factor, okay? So let's go ahead and see how this would work out. Basically, question B, determine if the following expressions are a factor of the polynomial. So if x plus 1 is a factor, that means x equals negative 1 is the potential 0. So all we're simply going to do is plug in negative 1 into this polynomial. And if we get 0, then we could say x plus 1 is a factor. Okay, so anytime you have a negative number raised to an odd power, that's going to be negative. This then becomes positive, negative, positive, plus negative 1. Well, let's just turn that to a negative. Negative 1 plus 1. All right, so we have negative 1 plus 1 plus 1 minus 1 minus 1 plus 1. Okay, so obviously that goes to 0, that goes to 0, and that goes to 0. And again, guess what we get? 0. So x plus 1 is a factor. All right, so now let's go and do this with 2. So that means my k would be positive 2. So I'm going to plug in 2 to the 5th power minus 2 to the 4th power minus 3 times 2 squared plus 3 times 2 plus 7. All right, so 2 to the 5th power is 2 times 2 times 2 times 2 times 2, which is going to be 32. Minus 2 times the 4th power, that would be 16. Minus 3 times 2 squared, which would be times 4, plus 6 plus 7. So that's 32 minus 32 minus 12 plus 13. Well, obviously that goes to 0, and you can see my answer is going to be a positive 1. So therefore, x minus 2 is not a factor because you can see that it does not equal 0, which kind of brings us to our next theorem, which is the remainder theorem. So if a polynomial function f(x) is divided by x minus k, then the remainder is r, which is f of k. So again, that's really saying the same thing. The only difference between the remainder theorem and the factor theorem is if r is 0, then that tells us it's a factor of the polynomial. But a lot of times the remainder theorem is helpful because, I might just say, is something a factor or what is the remainder? And you don't want to do synthetic division or long division. So, if k is equal to 1, then you could say like the factored form would be x minus 1, right? But nobody wants to do long division, that into that, or do synthetic division with that. I have students do it all the time though. The easiest thing to do is just plug in our value. So 1 to the 14th minus 1 to the 7th plus 3. So 1 to the 14th is just 1 minus 1 plus 3. So you can see the remainder in this case is 3, right? That is our r. r is equal to 3. That is the remainder. Obviously, via the factor theorem, that tells us that x minus 1 would not be a factor if that was something I was going to ask you. In this case, we have a negative 1. So again, we're just going to want to play the same kind of idea. That would be a factor of x plus 1 if we were going to test if something was a factor. So therefore, r is equal to negative 1 to the 7th minus negative 1 to the 5th plus negative 1 cubed minus negative 1 minus 2. So a lot of negatives here. So we have a negative 1 minus, say a negative 5, or negative 1, sorry, minus negative 1. So it's plus a negative. And then that would turn into a plus a 1 minus 2. And so let's see here. That goes to 0. That would be, so negative 1 plus 1. So that goes to 0. That goes 0. And you're left with a negative 2. So the remainder in this case would be negative 2. So again, x plus 1 would not be a factor if that was the question. All right, so now let's kind of come full circle again. And basically what we're going to do is now I'm giving you the zeros, and the main idea is writing the equation given the zeros. So we kind of talked about this in the beginning of the lesson, that writing the linear factorization. If we can write the linear factorization given our zeros, then all we got to do is multiply them to figure out the polynomial in standard form. And really the only difference here now compared to what we did for rational expressions or rational zeros is now we're dealing with these irrational zeros, so we know we have to include the conjugate pairs. If I have positive square root of 3, then I'm going to have negative square root of 3. If I have 1 minus 2 square root of 5, I am going to have 1 plus 2 square root of 5. So even though I don't provide it, we need to know that those exist. So kind of following again the pace that we did for the last one, or last time we did this, you basically can set each and every 0 equal to x. Okay, and then basically now we can just go ahead and write them equal to 0. Oops. So we can have x plus 2 equals 0, x minus square root of 3 equals 0, x plus the square root of 3 equals 0, and x minus 0 equals 0. Now again, remember this has a multiplicity of 2, so I'm going to raise that to the second power. We don't really need to write the x minus 0. We can just write it as x squared, right? And now let's go and write this as a product of its linear factors. So I'm going to start off with an x squared times the factor x plus 2. And then I'm actually going to multiply these. Well, let's actually write it out. X minus square root of 3 times x plus the square root of 3. Hopefully you guys recognize, though, that is just the factored form of x squared minus 3. Hopefully, if not, you can multiply them out. Hopefully you can multiply this out, so that becomes x cubed plus 2x times a x squared minus 3. All right, and now we just have a binomial times another binomial. So this is going to be x to the 5th minus 3x cubed plus, and let's see, a 2x cubed minus a 6x. And then let's just combine my like terms here, which is x to the 5th, a minus a x cubed minus 6x. And voila, there we go. Now the next one, I'm going to do the longhand method, and then once we do complex zeros, I'll show you a shorthand or a trick for this. But I think the important part is first just to, understand them again as they go. And again, we see this 0, which x equals 1 minus 2 square root of 5. Therefore, x equals 1 plus 2 square root of 5. X equals negative 1, and x equals positive 1. Set these equal to 0 is going to be x minus 1 plus 2 square root of 5 equals 0. X minus 1 minus 2 square root of 5 equals 0. X plus 1 equals 0, and x minus 1 equals 0. Okay, so therefore, the product of my factors here, and I'm writing this all out here just so you guys can see this. And again, I recommend, if students have a problem like this, to do shorthand. I just want you guys to all see what exactly I'm doing. So that's why I'm taking the extra time to write everything out. Okay, so now I need to multiply everything out. Now, even though these look really confusing, if you think about it, all they really are is just a trinomial times a trinomial. And if you remember, where did they come from? They came from basically using the quadratic formula. So they are going to produce us with a trinomial. And all I'm going to do, 2 square root of 5, I'm just going to put 1 up top and 1 along the side. And I'm going to multiply this using the box method. Okay? So again, you're just finding the length and the width for each of these boxes. So x times x is x squared. X times negative x is negative x. This becomes a 2x square root of 5. This is a negative x. That becomes a positive 1. This becomes a negative 2 square root of 5. This is a negative 2 x square root of 5. that becomes a positive 2, square root of 5. And then this would be a negative 2 times positive 2 is a negative 4. And a 5 times 5, that would be a negative 20. All right, but the nice thing about this, again, is our like terms, guys. That this is going to give us an x squared minus 2x. That's a negative, that's a positive, so those terms are going to cancel out. Those terms not cancel out, they're going to add to 0. These two terms add to 0, and then I'm left with a positive 1 plus a negative 20 is a negative 19. And then I'm going to multiply that by a x squared minus 1. Now again, I'm going to use the box method again for this. You could probably use distributive property and you'd just be okay. But I just kind of feel like doing the box method again. So in this case, I'm going to say, well, this one's x squared minus 1. And then this one's going to be x squared minus 2x minus 19. Therefore, that gives us x to the 4th. This gives us negative 2x cubed. This will give us a negative 19x squared. Negative x squared. Let's see, that's a positive 2x. And then this one would be a positive 19. Okay, now again, notice that we don't have everything perfectly on the diagonals, but at least good enough that I can simplify my terms here. So I'm going to have an x to the 4th minus 2x cubed. This gives me a negative 20x squared plus 2x plus 19. And that would be my standard form of my polynomial. So there it goes, ladies and gentlemen. That's kind of full circle here. We talked first about finding the irrational zeros without factoring, then with factoring, then using division, and then understanding division without doing division via the factor and remainder theorem, and then writing the equation given the zeros of irrational zeros. So hopefully that helped, but I'd love to hear any of your comments, guys, from things that made sense, maybe some things I left out, or some things that maybe you have some questions on. So either way, look forward to seeing you guys on the next lesson, and thanks so much. Cheers.